This tutorial. My name is Lorena Barba, and Gil here is my brilliant PhD student, and he's the author of the exercises you will see today, and I'm really here as I have been his tester of the materials, and also will be his assistant today. So officially the instructor here is Gil, but we also have we have one official volunteer helping out. Harsh is right here, and we have two additional volunteer crushers would be, I think, the category, and that's Jonathan and Aaron. Andre, maybe we get Andre. Officially is a volunteer as well because he lent us the computer to fix the projector connection problems. So we have a lot of help, and we want the first few minutes to get oriented. Gil is going to go through what the idea for this tutorial is, and then we want to make sure that everybody is on board with all the installation, all the materials on their computers, and with the helpers, we're going to walk around making sure that you have everything. So let me welcome Gilbert.
Thank you, everyone, for coming. Happy to have you here. I'm going to come back to the title slide in a second. For now, if anybody doesn't have the repository cloned and all the dependencies installed, now is the time to do that. There are instructions in the README at this tutorial. Does anybody not have it? Actually, we just check. OK. So that's actually pretty good. Are you on your way?
I just went to the wrong convention center.
Oh, man. All right. OK. So I think what we'll do is have maybe Aaron can help you out. If I'm going to take these instructions off, but the link is, if you've got the Slack Numba channel, it'll be there. So my name is Gil Forsyth. Professor Barba and I are from George Washington University. The title of this tutorial is Numba, Tell Those C++ Bullies to Get Lost. What I mean by that is not that C++ is innately horrible or terrible. You know, your mileage may vary. But that I think until recently, the idea has been that Python is great, and it's this great glue language, and we love using it. But if you have any serious numerical work you need to do, you need to fall back to Fortran or C or C++, and you end up dealing with Swig, and then your life falls apart. Swig is great, by the way, too. It fit, it was a solution to a really big problem. But and I think my take, anyway, is that that's no longer the case, and we don't have to do that anymore. And so hopefully we'll take you guys through kind of how to speed up your code without falling back on things like C and C++. And yeah, we'll take it away. A quick note on style. This is just my thing. I'm sorry. So I do explicit imports. I don't abbreviate things. I know that the convention is very much NumPy as MP. Aaron and I have had many rounds on this. And I get it, but like then you import SciPy, and is that SP, or should SciPy be SP? And you get... Yeah, so it's a couple of extra characters. We all have really good tab complete, so... I'm mentioning it only so that when you're going through exercises, I imagine there will be some muscle memory that makes you type NP a lot, and it won't work. So either change the imports, don't do that, or just, do my way, which is better. Much more readable, cleaner, prettier, yeah. So what is Numba? If you're here, I imagine you might already know, but just a quick thing. Numba is a just-in-time compiler for Python. So it generates optimized machine code using LLVM. It is made to integrate with the scientific stack, and I think that is a big, good thing to be doing, and it's awesome. Numba is also just, it's like one of the Continuum sponsored open source projects. So they are doing us this huge favor by putting really awesome people on it, and Stan Sievert's team is amazing and incredibly responsive, and I can't say enough good about them. They actually implemented recursion for me, which was cool. It's a little too late for this tutorial, but Numba is not a full replacement of the CPython interpreter, like Piston and PyPy and Pigeon and all those. And it isn't magic, but it does work very well, and it is designed specifically for mathematical heavy lifting, whereas these others are more kind of general purpose solutions. Also, Numba specifically targets your CPU. So I'm actually running this off of my dev machine back in DC. I have a 6-core i7 with a bunch of instruction sets that you probably don't have on your laptop CPU. So it just like the speedups will be slightly different depending on what you're working with, and that's actually true whenever you're using this. So it's good to just play around with it, experiment, see how it works. You'll still get speedups. It's just how much of a speedup might depend on SSE3 or SSE4 or whatever thing you have on your CPU. So this is going to be a do as I say, not as I do for this particular tutorial. You need to write tests when you're using Numba. You should always write tests, right? We all know that. And we say, yeah, and then we've got those projects that are completely uncovered. You really need to do it with Numba because when something goes wrong with Numba, the problem is that and we'll see more of this as we go in, but just to give you, the traceback, it's going to break inside Numba, not inside your code. So it's not going to tell you much of anything helpful. Like you can see, oh, it failed at this like lowering step percent. Wait, where? But what line of my like function? You have no idea. It's not going to tell you. And so as long as you string Numba functions along, if you have something that's completely JITted and you run it and it breaks, all you know is that it's somewhere in your code. That is as specific as it is. So write tests so that when things break, you know where roughly they're breaking. A lot of us use NumPy a lot, I imagine. We're going to be writing a lot of loops, and it's going to seem a little bit weird, I think. I mean, it seems weird to me. It seems almost not Pythonic or not NumPythonic. So those are all my caveats, and with that, we'll get started. So if all of you would like to go into the notebooks folder, you're probably already there, and open up.
Well, let's make sure that everybody's there. Everybody's got their notebooks? Yes?
Mine's blowing up on the content environment set up. It doesn't like your YAML file.
Oh, another one of
There's
those.
a, so we posted a solution to that in the issues thing.
Yeah, there's just if you go to the issues in the GitHub repo, I've just got like a one-liner for installing the right versions of everything. You can just like a conda install all these things. That should help with that. Yeah. I will. I'll open the notebook and kind of see how it looks, and we can. Oh yeah. Well, that's a little too small, isn't it? How's that?
Okay,
Is that readable-ish?
We have a channel on Slack, and I'll be monitoring, and please feel free to post questions there too.
One more thing I forgot in the intro, I sometimes talk very, very quickly. And if I'm doing that, feel free to raise your hand and say slow down. It's totally fine.
Slack, that is talking too fast, and that will stop slow.
Yeah, that's also totally fine. It'll be totally anonymous, except I'll check afterwards who it was. Okay, so we're actually not going to start with Numba at all. We're going to start with, I'm going to get the toolbars out of here so you guys can see this a little better. Actually, I'm going to leave that toolbar. All right. So you need to know when to use Numba. That's the first thing. You don't want to use it everywhere. Python can be made to run very quickly. But as we know, things like nested loops are a bad idea, usually. But the alternative to that is that if you try to make everything faster, even things that aren't actually hurting you, you're sort of hurting yourself. It's a technical debt. You're intentionally obfuscating code that doesn't need to be, sped up or had trickery done with it. So what you want to do first is find where the bottlenecks are and concentrate your time and your energy on those things. That's really what you need to do. So we're going to look at 3 tools here really quick, just as an intro for anybody who hasn't worked much with profiling tools in Python. The first is cprofile. That's built-in the Python library. Line profiler, hopefully you've installed. I will turn my phone off. And time it, which is not really a profiling tool, but we're going to use it a little bit just to investigate things as we go along. All right. So here is some really bad code. All right. So we have a bad call that sleeps for half a second. Can you guys read this? Okay. I guess you're on your computers too, don't you? A worse call which sleeps for 1 second. We have an instance check. We have a matrix multiplication for no reason at all. And then what the actual function does, which is just sum from 0 to n of whatever integer you give it, and then returns that after sleeping for no reason. If you're running Python 3.4 and you run this, it'll break because it's using the at matrix multiply decorator. You can just change that to a numpy dot. But we're going to run this, and lo and behold, it works, but it probably shouldn't have taken that long. So when we want to start looking at how to figure out what's going wrong, even though I imagine right now we all know, you start with cProfile, which will give you sort of the top-level view of what's taking time. All right, so you can just import cProfile, and then you pass it a string with what you want it to run. So in this case, we're going to run exactly the same command, and we will get our output. Oh man, this is a little wonked right here. I'm going to make it a little smaller just so the wrapping isn't so bad. Hopefully that's not too terrible. I'll make it bigger again when we're past this. So this is giving you the number of calls of each function here. Also, when you run it in a notebook, there's this weird thing where, well, it's not weird, it's just telling you that which cell and which line of which cell is responsible for each call. And you can see that the second line of the profiling there, bad call takes, 0.5 seconds, and worst call takes 1 second. And this isn't a huge surprise to us at this point. But this is where you start. You want to see where are you hurting in terms of which function is costing you time. And that's your first sort of overhead view. So then once you know, or you have a place you'd like to start, like looking a little bit deeper, that's when line profiler comes in. Well, where cProfile tells you which function is taking how much time, line profiler does the same thing for a given function, and it shows you line by line where the time is being spent and what's costing you. So in the notebook, you just need to do a load.ext line profiler, so it makes the line profiler magic available in the notebook. And then the syntax here is that you do %lprun. The -f says, this is the function I want you to profile. I guess I'm missing a cell in here for some reason. Yeah. All right. Okay. So I've just written this out here because it's supposed to be there and it's missing. But so the syntax is lprun -f by 1 or more times is the function you then want to profile, and then you need to give it something that will actually trigger that function to run so that it has something to work with. So in this case, I'm just going to do the numbers up to 13, and this will create a pop-up that is probably not visible, so you can bump it out into an external window. Okay, can you guys not see that at all, probably? All right, I can't zoom plain text, I'm sorry. If you're looking at it on your machines, though, you can see that we have the line number of the code, the number of hits that each line gets, the time in microseconds that each line takes, and per hit. And then really the column you want to concentrate on is percentage time, because that's going to point you sort of to what where the issues may lie and what you want to start working on first. In this particular case, it's not super surprising that bad call and worst call are taking the vast majority of the time there. So given that we see that those two functions are what's hurting us, then the next step is then to look at those two a little more deeply and kind of keep digging until you find something you can work with. So if you want to profile two functions at once, it's the same thing. You just pass -f for the first function you want to profile, -f for the second function you want to profile ad nauseum, and then still some call that will trigger those. So in this case, it's still going to be calling sumulate. And if I run that, then you will see that this is actually not super useful since we know what's in them and they're one line each. But you get a report for each function that you've profiled. And this is where if there were some heavy math in here, that would maybe show you the line you need to look at, or maybe a subfunction that you can start to accelerate. since you may not always want to look at everything right away, you can also dump these files into a text file with a -t flag there, which is the same thing. It also pops this up. And then you can load that text file if you want, and you get nice syntax highlighting. And this is the same thing we saw before. It's just the line-by-line profiling results. Since we don't always, sorry, is everyone okay at this point? Take that as a yes. We usually actually aren't profiling things in a notebook. So what is more common for me anyway is you profile when you're working with a script or a module or a package or something, and you're most likely on the command line where you've got your text editor. So in that case, I'm just going to open up a terminal here. Yeah, sweet. So if you have a text file, can you guys see this? Okay, cool. I don't think I can change that easily at the moment, sorry. So I have copied that really terrible script I wrote into just a .py file here. So it's the same thing that is in the notebook. And if you want to profile a given function, in this case we want to profile simulate, all you do is add the @profile decorator. And the only other caveat is, since you're going to be running this from the command line, if you don't have like a if name equals main at the bottom or something like that, it's going to profile what it takes to define those functions and put them into a namespace and then exit the interpreter, which is not useful. So make sure you're actually running whatever you want to profile, same as you pass it with the notebook version. So if I do that, then you do a kernprof-l, and then give it the name of the script that has that. And that will write that profiled, the profile results to this file that has the same name as the file with the .lprof suffix. And that's so if you want to profile a bunch of things, you don't need to do them one at a time. You can just do them and then go through the results at your leisure. And then if you actually want to look at them, you just do a python-m, what is it? Yeah, line profiler. And sorry, it's getting cut off there. That's badscript.py.lprof. You pass it the name of that file, and that will show you something which, again, is familiar, which is just the results of the profiling.
Hey folks, quick web chat. Everybody following along? Who is right on with Gil and is just typed in code alongside with him, or is following at a content speed? Is he moving a little too fast? Raise your hand.
Or maybe you could take,
Okay.
maybe you could take a minute.
Sure.
For everybody to do it
Take a minute.
in
Yeah.
their own notebook, right? Execute and actually follow along and obtain the results yourself.
Oh, sorry, if you want to do the terminal pop-up in yours, sorry, just change the port number to 8888 or whatever.
I still need to set up
Oh,
something
okay,
like that.
sorry.
Oh, do the terminal pop-up things?
Yeah, if you want it within the notebook, just, to be, have it be fun. Just make sure that it's,
Or you could just open another terminal with the tutor and the tutor
yeah.
app.
Oh, in the notebook? Yeah, I just did I have an iframe, and you,
You can also open a new notebook from the regular dashboard.
yeah, if you're on your notebook list, you can go to new and just choose terminal instead. I just did this to have it in line.
So this is apparently an issue with Jupyter Notebook 4.2.1, the inability to do the line extension magic. So I just posted into the Slack to do a pip install of the missing extension, which is Jupyter ND Extensions Configurator, which is somehow not in, I suspect, the conforge recipe for the notebook. So I suspect there's an issue with the conforge recipe.
That is good to know. Sorry about that. Thank you, Aaron, for tracking it down. I will add that also to the README afterwards, so if you guys come back to this, you can actually see how to get it working. No, it's part of IPython. It should be anyway.
Yeah, it's not working on mine.
How do you see them? Sorry. Right at this line here. So Python-m line_profiler, and then the name of the file that's been generated. Okay, so I'm going to move on if everyone has had a little success, hopefully, running a profiler run or two. Cool. All right, so the last thing, just a quick run through if you haven't used it. This is just helpful in notebooks for just comparing rough performance between non-numbified things and numbified things, which is the time it magic. Time it has its issues. I have here command line version, command line options to alleviate some of the concerns people have raised about time it, which is that it only runs a certain number of times, or it only returns the minimum time, or it disables garbage collection, which some people feel that might, unduly impact what the actual performance will be. So these are just 3 commands for your reference to undo each of those things, or however you want to deal with them. If you have a line magic, it's a single percentage sign, and it'll just run that however many times it thinks it has to reach a certain total time, and then it'll tell you roughly what the timing is like. So just, this assignment into X is 12.5 nanoseconds, which is pretty fast. Similarly, a cell magic, you can just list a number of lines in a row, and it'll time all those things. And one useful thing, I think, is if you pass the -o file, or -o flag, rather, it will return the time it result into a variable so you can play with it. The -q flag is just to quiet the output since I'm saving it into a variable anyway. That sometimes disagrees with OSX, so if it does, just take it out. So if, though, I've run that and I have this -o, then A now has all these attributes here that you can take advantage of. So if you want to see the timings from all the runs, you can do that, or you can look at the worst run or the best run, or how many loops it took. So it's just a way to programmatically compare things if you want to do that. Okay. And that's all I'm going to talk about retime it and profiling. People feeling pretty good right now? Cool. All right. So now we can finally dig into Numba a little bit, which is probably why you're here. Okay. So the first thing we're going to be looking at is JIT, which is just in time. So this is what you do when you find a hotspot and how you start to improve its performance. Right. So here I have a pretty naive function that just sums every element in an array and returns the sum. And I'm doing it in a way that if you've used Python at all, this is not a good way to do this, clearly. I have like 2 nested for loops. It's going to be slow. This is a really bad way to do this. Don't do this if you're not using Numba. So if I just sum, I'm going to just generate a random array 300 by 300, grab the sum, and then we'll see how long that takes. So 25 milliseconds, which in the grand scheme of things is pretty quick, but if this gets bigger, it's really not. And so to use JIT, the first thing you do is just import it. So we're going to do from Numba import JIT. And there are 2 ways to JIT something, to JIT a function. The first way is as a function call. So as you can see here, this line, sum array Numba equals JIT open close paren. I'll talk about that in a second. And then you give it the name of the function you want to accelerate, which in this case is sum array. And I have now created a JITted function called sum array Numba. And I can pass that, the same array, and we get the same answer. And now I'm going to time that version. And that says 73 microseconds. And if we check that out, that's a 338 times speed up. Now, admittedly, this is a bit of a contrived example, and we have nested loops, and you wouldn't normally do this, but it gives you an idea of what can start to happen with this. That is, I've added 1 line of code, and it's just a decorator, and that's it. And now, sorry, it wasn't a decorator, I lied, I'm talking about that in a second. But I added 1 line of code, and it's fast. The more common usage you'll see of JIT, and the little bit like cooler looking version or something, is to use it as a decorator here. So you just write @JIT at the top of the function you want to accelerate. And then that's it. Now that function is a JITted function and has that similar performance. In terms of why you would use one way to JIT versus the other, if I'm experimenting with something and I want to see how if it's going to speed up or if it's not, the Numba is not always the best solution in certain situations. I like to use the function call because I keep the old function around. I don't overwrite it, so I can compare their performance, see how they both work, make sure that they return the same answers. Once I know that I like that, then I'll probably just go and put the decorator in because it's easier. Yeah, also of course, like NumPy has a sum method. We would just use that normally, and that is 33 microseconds. So this is not hugely surprising. NumPy should be faster for something like this, and it is. It's a incredibly well-optimized code. Yes?
When you spend a half a minute to explain why it should be faster,
Why NumPy should be faster?
Yeah.
Just because, so I mean, Numba is, I'm going to talk a little bit in a second about how Numba is working, but for relatively basic operations, NumPy is mostly C and has been kind of hand-tuned and works very well, and is also like, tying into the underlying BLAS, and people have sat there and been like, how do we make sum work really, really quickly? Numba is just looking at whatever code is there. It's inferring the types of things and then trying to compile it down. So if I JIT something that is like A equals 1 plus 1, it's never going to reach, I mean, it may get close, but it won't be as fast as just CPython because there's not really anything there there's no there. You don't need to, there are fewer places you can actually pick to optimize. Not that we're picking, that Numba's doing that, but we'll see examples later on of when that assumption breaks down. And where Numba is definitely the way to go. But if you're just talking about like built-in NumPy methods, especially ones like to sum or to do a dot product or something, those will almost always be faster. Yes?
So if you want to address this later, that's fine, but I'm just curious about the sort of interaction between NumPy and Numba. So like if you have a function that has a mix of like NumPy code and then some other stuff, is it okay to sort of wrap a JIT around the whole thing and then let JIT figure it out, or is that let Numba figure it out?
The short answer is yes, it's fine. And I will talk more about that in a little bit. But for now, Oh, sorry, yeah. Numba compiles something, just a quick note here. Numba doesn't compile something when you add the decorator and run that cell or execute that. It compiles it the very first time you run the function after you've written it, and then you give it some inputs. So sometimes if you're using time it or something like that, you'll get a message. I think I got it above that. One of these runs took 4,000 times longer than the others or something, and that first run is the compile time hit you take. Now, as long as this kernel is open, it's going to keep that available, so every other time you run it, it won't have that penalty. And the penalty is also usually really small, but just be aware of when that happens. Now it's your turn. So if you can click the link there, and that'll open up an exercise notebook, which is just a quick JIT exercise. So I have this well-traveled Mandelbrot fractal generation code here, which many of you may have seen before. I've commented out the line that actually runs it because I can tell you that if you run it without using Numba, it takes a really long time to go. So I'm going to give you guys about 5 minutes, and I'll just say try to use the JIT decorator to make the Mandel and or the create fractal functions faster. And my one tip is don't overthink this. Just for comparison too, because you guys don't want to run wait for a break to run the non-JITted version on your laptops if you want. I can tell you that my machine, which is well, it doesn't matter, it's 6 cores, but it's a Core i7, takes about 15 seconds to run this as it is right now. So that'll give you kind of a mark for when you have your numbers.
Time it does it to real time.
Yeah, so if you run that with time it without JITting, it's going to run it at least 3 times, which means you're going to be sitting there with laptops, even really fast ones, at least a minute. So that's why I'm suggesting you don't do that. Yeah?
Is there an easy way to capture the output of time as like a variable?
Yes, sorry, the question is there a way to capture the time it output? Time it, yeah?
Time it or time?
With time it, if you pass the -o flag to it before you give it whatever it is, then you say like result equals %time it -o thing you want to look at. It'll drop the results into that.
Okay, thanks.
Mm-hmm. Yes?
Can you just say like a brief one-sentence thing for totally news who don't know how decorators work?
Oh, yeah, sure. So decorators they're just Python functions. And they are, wow, this is on camera, awesome. But so they are functions that basically are written in such a way that if you add the decorator to a function, it gets wrapped around that and it does whatever it's going to do. So you could have a decorator that always adds 1 to the result of a function, and the code for the function that does that, when you define that decorator, it would just say, do this, get output, add 1, and then you add that decorator, and then that function will always return what it would normally return with its result incremented. The JIT decorator is really complicated and not that simple, but that's the rough idea. It's just a way to alter the behavior of a function without editing the actual code of the function. In the same way that the profile decorator from Line Profiler works, it's just it's a way to change behaviors.
So it's basically a wrapper.
Yeah.
So I can wrap any function
More or less.
I'm going to put everything you just said on the
That's totally fine, and it'll be on YouTube too, so you can cite it. It'll be good.
And there are also built-in ones like class method.
Yes, there are, and abstract method and static method. Yeah, there are plenty of built-in decorators. If you want a really much better explanation than I gave of this, you can check out Anthony Skopat's and Katie Huff's book. It's top-notch. What is it? Effective computation in physics. Yeah, it's actually just effective computation. It's not even just physics. It's awesome. And they're better at this than I am, so yeah. Okay, so if people have gotten some results from this, I'll show you my incredibly complicated solution to this one. I really wish there were Vim key bindings in this notebook. Yeah, so I just added @JIT decorators to both of those. Yep. And lo and behold, oh, well, sort of behold. Ugh. That looks Mandelbrot-y. And so I told you guys, and if you believe me or not, but I told you that it takes about 15 seconds on my machine usually. And we run this with the JITted version, and it's 42 milliseconds. So it's a significant speed up, I'd say. Yes? I sure am. Viridis? I could talk about Viridis for the rest of the tutorial, and people would just start walking out. It actually represents data correctly. Like I mean, Jet is an abomination. There's a great talk from SciPy last year. Was that it? When Nathaniel? Yeah. So Nathaniel Smith, last year's SciPy. Also, it has fidelity for people with color blindness. So I especially really love it for that. Yeah. Yes. Yeah. That's the man right there. So. Okay. So that's that. All right. Now we're going to delve a little bit into how all this works, just so you have a better understanding of when it doesn't work, what's going wrong, hopefully. And I think after this, we'll probably take a break for 10 minutes so people can stretch their legs and absorb. Yes, sorry.
So, absolutely amazing, but what's, are there any bad things that you use this for loops?
I will try to address that a little bit later. There can be, I wouldn't say that there are inherently bad things. There are times when you wouldn't use it. Just as a quick, like, you know, again, if your code says 5 times 5, don't use it. I mean, it's just, it's not worth it. And it does make your tracebacks useless when something goes wrong. So that's yeah. Okay. So how is this working? At very high level, so if I create this trivial function here that just adds A and B together, and then I have to run it once to make sure it's actually compiled. So I'm just going to do that. Hey, we got 2. Cool. So what Numba is doing, what that decorator, JIT decorator does, is actually examines the Python bytecode, that the C Python instructions, and then it translates it into what they call an intermediate representation, which is just a way for it to then make use of the LLVM compiler, which is what translates this into machine code, and that's what makes it fast. If you want to see how it's doing that, kind of what that intermediate representation is, after you've run the function once to compile it, then there's this inspect types method, and I will now show you the output of that. Don't worry about everything that's happening here. A lot of it you can gloss right over, I would say. The important thing, I think, is just noticing that when you have variables, that they say things like int64, because I gave it 2 integers, or that they would say float64 or something. If they are types that you can define, that are sort of known integers, floats, things like this, that is an indication that that's something that Numba really knows how to speed up well. It will tell you something else, which we'll see shortly, if it doesn't know how to do that. Also, I'll just point out that if I run this again, but this time making them explicitly floats, you can inspect the types once more, and you'll see that on the top right here, at the very beginning of the head, again, it just says add int64 and 64. If you scroll down, running it a second time, it now has a float64 version. So as you send in new variable types, it will, on the fly, generate these accelerated versions that make use of them, with the big caveat that you need to pass them in order of like most to least precision. So if I run this with floats first and then send it integers, it's just going to cast them to floats. So if you need something to preserve its type, this is just something to keep in mind. There are better ways to do that, which we'll look at a little later on too. If you're just curious about what on earth going on, you can actually take a look at the LLVM code that's being generated by this like one-line function. It's a dictionary, so this is just a better way to look at it. And yeah, there's a lot of, you know, when you have guys with break, you can take a look at it. That's what it's doing, which is sort of incredible. Now, there is an issue, not an issue, but we got to look at this. So when you want to, for instance, if we're operating on object attributes here, so I just have something that's going to do a cumulative sum, n2 times, n squared times, and I have a dot x plus b dot x. And then I create this class which just has this x attribute, and that's it. And I pass them in. So this is the pure Python version, 27.9 milliseconds. And now I can JIT that using the function form and run it again. And that's 34.8 milliseconds, so it's slower. Which is not what we want. That's not what we're looking for, right? And what's happening is apparent, or at least a little more visible, if you look at the inspect types of this function. And what you'll notice here is that you don't see int64 or float64 anywhere. You see PyObject. And what that is Numba falling back on this object mode that it has. It basically says, rather than just giving up the ghost and dying, those mean the same thing actually, but it's making it work to preserve its functionality, but it's not able to make things fast. It's basically saying, like, I don't know how to define that object. And so I'm going to just keep it as an object. I'm going to run in basically native Python. So if you do this, and let's say you have a function with a lot of nested for loops, you're going to take a hit because you weren't expecting to use nested. I mean, the whole idea was the nested for loops would be fast because Numba's going to work. If it doesn't, it might leave you hanging for a while.
Can you explain why it would be slower than using it?
Well, because you're also taking a hit on. Let me think about that and get back to you. It is, sometimes it's just because you're writing the code in a way that you normally wouldn't, but other times I think it just has trouble handling it. I'm not sure of all the internals with there. Yes?
Is there a way to cast your object in a way that Numba knows what it is?
Yes and no. That you can, well, no, actually, you can't. If it's unsupported, it's unsupported. I'm going to talk briefly now about kind of what the rough umbrella of what's supported is. Really what you can do is tell it to, I want you to tell me when this isn't working right, instead of just running. So there's two modes in Numba and JIT, and one of them is object mode, which is what we've just seen. That's the PyObject business. The other one is called, oddly, no Python mode. And what no Python mode is just it's basically the supported subset of Python that Numba knows how to accelerate well. And it covers a lot of things. You have to look for stuff that doesn't work, like I did for that example. One of the big ones, I would say, is actually classes. It doesn't work with native Python classes. So that's a big caveat for now. I mean, they change every 6 weeks, so just keep an eye on the feed. It does support almost all of NumPy's built-ins, I think not all of the linear algebra submodule, but it does support a lot of stuff. It does not support list comprehensions, dictionary comprehensions, generators, and try excepts. So beware of these things.
So if you're iterating over a list or iterating over something in terms of an iterator, I guess then you're out of luck.
No, it's just specifically the list comprehension, like A for A in X where, you can basically explode that into a loop and have it do it that way, and that will work. But just the comprehensions themselves, they don't work. There's a link right here for if you want. These are sort of all of the supported features in no Python mode. And I'm going to say no Python mode a few more times. Really, it's just like when it's a way to think of it. This is when JIT's really working. I mean, when it's going to be fast, when you get fast code out of it, which is nominally what we all want.
So does that mean that in order to take advantage of Numba, we need to unroll our list comprehension?
Yes. And if you have, yeah, I mean, there are they strive for like the one line change and everything works great. We'll see as we go on that that often is not possible, but you should hopefully be able to make a minimum number of changes. And if you're profiling your code first, you know the few places where you need to change things and you don't end up rewriting your whole package.
And actually, there was a tutorial last year where he had us do an experiment where we did a list comprehension and then a loop version of it. And with newer versions of Python, the loop version is faster, which goes against everything that I had learned early on.
I did not know that.
So,
There's a question back there? I don't know. I'll check though, and I'll get back to you.
and sorry, one final question. So, what does JIT, the @JIT decorator do if you don't have JIT installed? Blow up, or is it just after?
It'll throw an error. Yeah, it'll say, it's an undefined function, so it's just it'll throw you an error.
But you can obviously write your own protection around it, right?
Yep.
Well, I was just wondering if you could like distribute code where JIT is somehow an optional.
Mhm.
And so you try import Numba, and if Numba it works, then you have JIT imported, and then if JIT doesn't work, then you can just define an empty function that just wraps it and does nothing. And if you want, you can even have that function warn and say, hey, Numba's not installed, this is going to take a while. So
Just for the internet people really quickly so they can hear the answer that Aaron's giving over there, is just that you can try to import Numba, and if it fails, just define an empty function called JIT and then pass a warning that it's going to be slow, but at least they'll know what's happening.
the scikit image repository is a really good place to look at how you can plug in backend kernels when things are available and use them, and then don't use them if they're not available. That's a really good pattern to look at.
Okay. Yeah, so there's a link here to the supported bits of Python that work in no Python mode, which is what you want. One other way to kind of figure out what isn't working is available on the command line. So I have to write this to a file and then run it as a shell command to see. But if I have a function here, the same thing where I have my own integer object class here, and I have a random loop here for reasons that you'll see in a second, and then I'm returning the a.x plus b.x, and I'm running it. So I'm going to save that to a local file, and then just note the bang in front of you, the exclamation point. That's to run it as a shell command. This is available on your command line. You just run numba -- annotate HTML, pass it the HTML file you want the results written to, and then the function, the script you want to run is on. And if you do that, then you can open that file. And this is really handy, actually. It will show you with some colors what Numba knows how to make fast and what it doesn't. So if it's green, that means that it can improve the speed of something. And if it's red, that's what's causing you trouble. You can actually click the Show Numba IR to that intermediate representation. And you can see this is actually an interesting thing about JIT too that I didn't mention before, that if part of a function can be made quicker, this is what's called loop lifting. It sees that loop and it recognizes the types of the variables in it. So just for this one bit, for I in range 100 under the green, you can see we got int64s, range iter, and 64, some bools. So that will be made fast by Numba. If we go down to the red text, then we see PyObject, 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 PyObject. So when you see PyObject, change something. That's what you want to try to remove in order to speed up your code. Sorry, is everyone okay right now?
How did you break open that text file, HTML file?
I've made a link to it right below you can click. So as long as you've run the same code. Huh?
So just click in the HTML.
Oh, I'm sorry. And the breakout, it's, I apologize. It's the thing that says Show Numba IR. Yeah. What you may then wonder, and I wonder too, generally you want to force no Python mode because that's what's fast. You don't want it to be falling back on this object mode unless it's just for compatibility or something. And so what you can do to force no Python mode is in the function call version, those extra set of parentheses that looked weird, that's where you can send in the statement that says no Python equals true. And what that does is that will work fine because it hasn't actually tried to compile it. When it tries to compile that function, when you give it, a call, it will throw an error. So it'll throw an error so that it doesn't let you run it. It's just to let you know that this didn't work. Also, right, I forgot. Did any of you install the toggle hiding traceback extension? Okay. So this is why I have it on, sorry. I'll run that again. The issue especially with Numba tracebacks, is that they're happening, as I was saying, in Numba. So this is not, to me, super helpful. And there's a lot of it. And really all that you need, or that you can really make sense of, for me anyway, are the last 2 lines at the bottom where the actual error is. So there is this notebook extension that will hide that traceback, or sorry, most of the traceback, so that you just get the error when you run this. So you might have to scroll a little more. It's a cool extension. I recommend it. Because most people want no Python mode, and because you get sick of typing no Python equals true all the time, they added in a shortcut. So if you just do ngit, so from Numba import ngit, that's just a shortcut to jit no Python equals true. And you can use it as a decorator or a function call. Yeah.
Sorry, you might have explained it or I kind of missed it. Difference between the no Python mode or how does that work?
So the no Python mode is the mode where all of the code in a function or something is known to Numba, and it knows how to make it fast. So it just means everything in there is supported by Numba's type inference and stuff, so that it can actually compile it down to fast machine code. And object mode is sort of this fallback compatibility thing, which will sometimes be slower.
Okay, so this is when you know that everything in your code is compatible with it?
Right, so if that works, then you know it's running in the fast way. And if it throws this error, then it's telling you there's something in there that's not speeding up. And that's when you might go to the annotate HTML or just look and be like, did I add an object, like a class in there somewhere? Or, yeah. Yeah, no problem. So ngit works the same way as jit, but also will throw that traceback error because it's forcing no Python mode. And I'm just going to gloss over these 2 things, but for the sake of completion, the other flags you can pass, these are all just keyword arguments. Cache equals true will, that penalty you take when you compile something when you run it the first time, if you do cache equals true, it'll write something to disk, and it will try to always use that first. So especially if you're actually running in production or you have something that you're going to run a lot, it's a good thing to put in. If you make any changes to the function, it will detect that, it will recompile it. But it's a way to preserve the JIT compiled things across kernels or sessions or what have you. And there's also a no Gil equals true flag. It releases the Gil. Yeah, my name's Gil. So it doesn't do anything else. It does that, but you have to then manage, there's no guarantees made about something being thread safe or whatnot. If you want to use it, use concurrent futures, which means use Python 3. Yeah, we're not going to look into that stuff. I just want you to know that it's there if you want to explore it on your own time. So yes, sir.
So we're using Python 2.5.
Yep.
How does this work in Python 2, like 2.7?
It supports 2.7. I don't, but it does. Yeah. Yeah. Okay, are there any other questions right now? And if not, I think we can take a 10-minute break or so, and people can grab some coffee and stretch their legs, and I can get my voice back. No? Cool. All right, if you all can open up the 4th notebook, it says direct summation. That's what we're going to be working on next. Okay, so here's our first semi-practical application. This is no longer just functions that add things quickly. Well, I mean, actually it is that, but with more going on behind it. All right, so I think probably a number of you are familiar with n-body problems, or at least a few of you. I mean, they come up in a lot of things. Molecular dynamics, astrodynamics, electromagnetics, weird protein orientation stuff. I mean, all over the place. And so there's some math there that I'm not really going to go over. Basically, you have to compare or calculate something between every possible pair of particles. So this is an order n² problem. And we're not going to speed this up algorithmically so much as we are with just brute force, because we can. So First, I have a sort of a pure Python, well, actually, sorry, the NumPy and Python version of this that we're going to kind of walk through, and then we're going to translate it to Numba and then see what performance is like. All right. So, I'm going to import NumPy. I have a class point here. It has an X, Y, and Z attribute, just coordinates that are randomly generated. And then it has a distance method that just calculates the Euclidean norm between it and some other point. And then I have a class particle, which is a subclass of point, that also just adds in 2 more attributes for mass and potential, which is phi. I should probably run those, shouldn't I? Yeah. So we're going to create a list of random particles and then define a function to calculate their interaction via direct summation, which just means brute forcing it, and then run it. So I have 1,000 particles here. I'm defining the mass as just 1 divided by number of particles, so they're all 0.001 mass units. And this is just a list comprehension to do that. So that's my list of 1,000 particles. And then you can see here this direct summation function. So it loops over every particle, and then for each particle, it loops over every other particle except the one it's on, which is what that array concatenation business is there. It calculates the distance between those 2 particles, and then adds it cumulatively to the potential by doing the mass divided by the distance. Okay. So let's run that. All right, so that was not like slow, but wasn't fast either. So let's get a time on that. I'm also going to save this time. You can or you can't. So 820 milliseconds is what that took, give or take. So let's load up the line profiler, which hopefully is an old friend to you now. And then we will profile direct sum, passing in that list of particles. Sorry again about the size of the text here. So it's actually surprisingly, it looks like it's that that distance function, although it's also getting hit, however many, almost 2 million times, so that might explain it too. So there's a lot here that we can work on. I mean, nested loops make things slow. So even if each individual hit is pretty fast, there are so many of them, so we want to speed everything up. This presents us with a slight problem, because as I told you before the break, Numba doesn't support classes. There is something called JIT class. I don't want to be remiss in not mentioning this. It's new, it's interesting, and it will be really, really great in a little bit, but it's just sort of not quite, in my very humble opinion, not quite ready for prime time. So, and I tried it anyway, and this version was faster, so I'm also showing you that for that reason. All right, so there are no classes, which is kind of a bummer, especially because having like attributes and things is really nice for literate programming, for actually understanding, instead of just being array 0, 0, and remembering that that's the mass. I mean, that's terrible. So one workaround that I really like for this is using custom NumPy data types. And so here's one. So what you do is you define this as a numpy.dtype. You give it a dictionary. You have a key of names, and a value is a list of variable names, or sorry, like attribute-ish names. And then you do need to define a format for those, like a type. So in this case, I'm just doing them as doubles. And it'll be easier to see what that's actually doing here. So if I then create an array of ones that is 3 long, and I specify the dtype as this particle dtype, which I've just created, then when we look at it, you'll see that there are actually 15 entries there, right? So each one is populating all 5 of those values. So you can then access those, for instance, the xth element of the 0th, I said element twice, the x attribute of the 0th element of that array, you can access just with bracket 0, bracket x, and I can set it equal to 2, and then you can see then that in that array that 0th, you know what I'm talking about, that the x thing went to 2. mass. Having seen that, if you guys will, I'm going to just pass it off to you now. So what I want you to do is if you click on exercise 1 there, it will open up a notebook for you to work in. Also, sorry, I did some anchor links there. So please scroll up and actually run the imports here. Otherwise, it won't work. But what I want you to do is to sort of duplicate the function that is in the original notebook that just defines these particles as having random coordinates. But now, instead of it being a class, it's just going to be a NumPy array of this custom D type, particle D type. And so it should take an argument n, which is sort of the number of particles you want to create. The mass of each particle, again, just do like n divided, or 1 divided by n for that. And just assign a random value to x, y, and z for all of them, initialize the mass, and the potential to 0. Yeah, so you can access, for instance, if you do, for p in this list of, this array, you can go through each value and set it. So I'll give you guys like 5 or 6 minutes to try to tackle that, and I can also roam and answer questions as we go. One hint too, a lot of us, especially people who use NumPy a lot, are trying, I find myself frequently, like, how do I make this fast? Undo those parts of your brain. Do it in like the worst way you can think of. I mean, not the worst way, but there's some unlearning you have to do sometimes here. Okay, guys. Anybody feel like they're like 15 seconds away and just need that extra little? Okay. I guess you never really know, though, right? Okay, so here's my solution. Live coding, not really. All right. So there's a couple of things I want to specifically mention about this, because I think they're cool, and all 6. Did anybody, and sorry, actually not even a show of hands, I'm just kind of like, make sure you added the decorator. That's something that I forgot to do a lot when I was starting off with this, because it'll still work, but won't be particularly quick. It's okay, that one you catch really fast the first time you run it. Also, so I didn't exactly mislead you guys, but I wrote this little code snippet up here, P of, bracket, quote, X, quote, bracket equals thing. That is totally valid and works, and that's really all that matters. If you want, only if you use custom D types and only in a JITted function, Numba will actually translate that. If you can use it like regular attribute access. You can just do p.x, p.y, p.z, p.m, p.phi. That works. It looks cool.
Only with JIT?
Yeah, so it looks cool. One of the issues here is that if you need to debug something, which often means removing the decorator because, again, the tracebacks are not helpful, that doesn't work in Python. Doesn't make sense to Python. So you go back, you have to either have both versions there, so it looks cool. You can use it if you're confident that it's doing what you want it to do. It may not always be the best option, but just so you know, it's possible. All right. So I just ran that. So I passed it 1,000 particles again, 0.001 for individual mass, and the 1 is just if I want to multiply the domain of the random numbers, which I don't. So. And we can see here, and hopefully you guys have something like this. If you look at it, that you do get an array. I'm just showing the first couple of elements, but you have an x, y, and z coordinate. The mass should be 0.001, and the potential should be 0. Okay. All right, so I'm immediately going to throw back to you guys again. There's no distance method anymore because we can't use that class. So you can go back to your exercise notebook. and write a JITted function distance that calculates the distance between two particles that have this d-type particle d-type. I've put here just the method from the class as a reference. Probably shouldn't use self as one of the, I mean, you could, and it wouldn't actually hurt it, but so just create a function that takes two particles and returns the Euclidean distance between them. Yes?
And so there's nothing preventing us from actually still having an object-oriented approach here and just grabbing the methods of the class and JIT, right?
I looked this up so I could answer this question. I forgot the answer. I,
There is nothing that prevents you, but it's not going to be fast.
Well, even if you JIT wrap the methods themselves?
So if you JIT wrap non-static methods, you're
Hmm.
passing the class object in.
So,
If you insist on having objects, which is, there's nothing wrong with them or classes, you can have classes that have methods that are not fast, but wrap JITted methods that are fast.
okay. So you have like a functional interface out here, so we're just calling
As long as the majority of the heavy lifting is done by static functions that do not require access or attribute access, you're fine. You can do it that approach.
So if you want to have like an object-oriented API, you can still do that as long as there are functions that here.
As long as it's wrapping Numba, as opposed to the other way around.
So,
Yeah.
so if you mess up during this exercise and so you get an error if you were trying to engine the thing,
mhm.
how do you go about figuring out what you did wrong?
Yeah. There's no, well, first, you should have written unit tests. No, it's, yeah, I seriously, especially if it's something that's like a little bit long, I comment out lines one at a time, and I just keep doing, I mean, there's, sometimes the last bit of the traceback will tell you something a little bit helpful. I have a couple examples at the end of kind of messages you may see. Oftentimes, they're impenetrable. It's just you have to go through bit by bit. So I mean, yeah, if you have unit tests, it can help a little bit. But even then, within like one particular like little something, it's trial and error. I know that the Numba guys are working really hard on a way to maybe mitigate that, but it's a pretty tricky problem, I think. Okay, guys, I think I'm going to move on. So again, here's my solution. I'm still using the attribute access style thing here, just because it's easier to type. But again, it's totally valid also to do this in a couple of different ways. Does this make sense to everybody? Okay. And not that it means anything, but I mean, I didn't time how much it takes with the first one, so we're not comparing it. 845 nanoseconds. All right, that sounds good. Actually, you know, it's not, because I already ran it once. So, yeah, it might go away, it might not. I don't know. It may, I've noticed some weird behavior with timeit, where it's supposed to not include the time to like copy things into the timeit namespace in the runtime, but sometimes it does and sometimes it doesn't. So it could be something like that, I'm not sure. No. Okay. And I have one more exercise for you guys to kind of round this out so we can get the whole thing going, which is to now translate that function that actually loops over all the particles and performs the calculation for the potential. So here is, for reference, the direct sum function as it was before. And you just want to make changes here to make it work with a NumPy array, which actually, and things like enumerate and stuff absolutely work in no Python mode, so you don't have to remove anything like the built-ins that are there. Yeah, that's it. So I think we'll do about 10 minutes for that, and then we'll check back in. And if anybody has questions or stuck on something, please, raise your hand or let us know so we can come by.
What's the difference between what's happening there and what you were calling the list comprehension earlier?
Here, which line of it?
For icon target.
List comprehension is, I mean, they do have very similar, kind of parts to them. It's just the way that they can be sort of parsed. Where did it go? So this is a list comprehension here. So basically, it's saying, I mean, you could rewrite this in a way that it would work. So you just be, for I in range n, particle list, empty list append particle m equals 1 over n or something like that. Yeah.
Somewhat related to that,
Mhm.
can you comment on the mistake I made, which was to loop over x, y, z to calculate the distance?
Yeah, so,
What is your mental model for Python lists? You should try to avoid them, or?
yeah. I mean, no, I mean, you can use them. I think you can create lists. Generally, you want to be a little bit wary of creating mutable objects inside of a JITted function. So there are parts of it that will work and there are parts of it that won't. And sometimes it's a toss-up. So I would say, again, it's sort of this unlearning. I mean, you want to be more verbose and more explicit most of the time because it's more likely to work in the first place. And also, it's then easier to comment out single lines one at a time as you try to get it to work. OK, so here's my solution for this. Again, I mean, when it seems unPythonic, right? Why would you have an if statement on every single iteration of the loop instead of an array concatenation? But the array concatenation actually costs more in no Python mode because you're getting down to machine code, so that if statement doesn't actually hurt you too much. It just takes, you have to unlearn, it's weird. But yeah, so in this case, we just loop over both sets of particles. At every single loop, I'm just checking to make sure I and j aren't the same. And this guy actually had a similar thing, just checking if r is greater than 0. Right? Or if the distance is greater than 0, which is also, but you can have checks at every instance of an inner loop, and it's not going to hurt your performance too much. By way of demonstration of that, too, I should say, that if we run this, we get 7.6 milliseconds. I don't actually remember the original time, but it's 107 times faster. So yeah, that's really good. I mean, it's nice and fast. One thing I want to mention that may have bit a couple of you, I'm not sure, is if you run, if I like have this direct sum function in no Python mode, which I do, it can't see other JITted functions. Sorry, it can't see other functions unless they are JITted. It's not available. It'll tell you there is a name error. It won't be able to find them. It'll be like there's no global thing with the name of that function. So yes, if you have in no Python mode. Okay, yeah, actually, I can. Here we go. So if I redefine this distance function badly, and then I run this. Give it parts. Come on. Untyped global name distance. It doesn't know what the distance function is because it's not Numba isn't aware. It's not part of Numba's scope. So this is this. Most of the time, you have a no Python mode function calling another no Python mode function. But this is also an instance where sometimes if you have something that's not no Python mode compatible, but it needs to be called by something that is in no Python mode, you might leave a plain @JIT and just to have it compile into PyObject mode just for compatibility with that other function. Yeah.
So is there kind of like a list of which functions kind of like enumerate that work
Yeah, it's there was a link in I think the second notebook that I have to a list of all of the supported Python functions, and there's a link on that page, which I can also add to the README later, of all of the NumPy stuff, which is also supported. As a rule of thumb, NumPy is almost entirely supported except for the linear algebra submodule. Okay. So, oh, sorry, yeah. What's up?
Can you say a little bit more? I'm sorry if you just explained.
That's okay.
So it just, inside that engine, it can't see the namespace, and that's why it doesn't see distance?
It can't see the entire namespace. Yeah, so yeah. When it's compiling, if it's not, Numba is aware of the things that the developers have built into it, and then other things that it has created, and that's it. So.
So you're saying wrap a plain engine around it and limit it?
Yes. Yeah, that's the first step. If you want it to be fast too, you might have to change it around. But yeah, that will at least make it work. Yes. We will get to that. We will get to that.
Did you push these changes to the GitHub at the end for that?
Will I push which changes?
Just the changes in the notebook.
Have I made? Oh, with the extra function there? Yeah, sure. I'm happy to do that. I will write that on a piece of paper, otherwise I'll forget. But I will do that. Okay, guys, let's take another like 10-minute-ish break.
I'm going to get started. I took out the mic so I could point to things over here in the screen, since I don't have a laser pointer. Also, this is just a breakneck introduction to computational fluid dynamics for those in the room who haven't been exposed to this before, because we're going to use this as the next example. And I'm going to be the one narrating this so I can give Gilbert's voice a little rest, and he'll be back with you at the, good. Well, he'll be back with you at the time of the exercise. So, how many in the room have some experience with numerical PDEs, or I want to see some hands to know exactly what. All right. With how many have heard about the Navier-Stokes equations? Everybody's, well, not everybody, but let's say more than 3/4 at least has heard about the Navier-Stokes equations. Actually, this is it. We say equations in plural because this is one equation in vector form equivalent to 3 equations in scalar form. This little u with a arrow on top means the vector of velocities in a fluid, in a flow. So we have 3 components. U, normally we write them U, V, and W as the 3 components, 3 Cartesian coordinates of a vector field velocity. And this equation represents the conservation of momentum in the fluid. So simply Newton's laws of motion applied to a fluid will produce this equation here. P, the P right here is the pressure, and nu over here, the Greek letter nu, is the viscosity of the fluid. So we assume that nu, most of the times we assume that nu is a constant, a property of the fluid. Rho is the density, also a property of the fluid. In this case that we are using as our example, we're talking about incompressible fluids, and so rho is constant. But P is not. Obviously, P is the pressure. It can change in time. It can change in space. As I said before, we have 3 components of this equation because it's a vector equation. So if you spell out vector U as U, V, and W, you can write this out as 3 scalar equations. We have 3 scalar equations, but we have 4 unknowns, U, V, and W, and also P. So as written, this equation could not be solved because 4 unknowns with 3 equations. If it was the case that we're talking compressible fluid mechanics, we would have in addition the equation of state. With an equation of state, we can then close the system. We have our 4th equation, and we're happy we can solve that. But in the case of incompressible fluid mechanics, we don't have an equation of state, and so what do we do? The trick, it's a pretty cool trick, as added there at the bottom, is the following. You take this equation, the Navier-Stokes equation, in vector form, and you apply a divergence to the whole equation. As you apply a divergence, you're going to get here, you're going to get, well, let's just say that you're going to get several terms that will have divergence of velocity equals 0, and I don't know if it's right there. Divergence of velocity equals 0, highlighted here, is the equation of conservation of mass for an incompressible fluid. And so once you apply the divergence to the Navier-Stokes equation here, a lot of those terms, you can cancel them out. And it turns out that when you do that trick, when you do that, it's very entertaining thing. Here's the Navier-Stokes equation written out for just 2 components. In the case of 2-dimensional fluids, where the velocity u arrow is u comma v, 2 Cartesian coordinates. This is how it turns out. So you can apply the divergence to each one of these equations, and out comes some terms that are of this form. Divergence of velocity, that is equal to 0, so you can cancel them out. When you do that exercise, it's very cool. You're going to get an equation for the pressure that has this form. It has the Laplacian operator on the left-hand side applied to the pressure, and here on the right, some terms that depend on the velocity. So what we do, and if you consider that all of these terms that depend on the velocity were temporarily in a moment in a suspending time constant, then we just write them as b, a constant. So this is a Poisson equation. It's a steady state equation. There's no time derivative, but a steady state equation can be solved iteratively, and this is what we do. The way to compute this iteratively is to start with an initial guess. Normally, we'll start with just p equals to 0 everywhere. You start with p equal to 0 everywhere, and then apply the Laplacian operator and iterate in what's called pseudo-time. It's not really time. It's simply we're iterating to try to find the steady state. And how does this work? So suppose we have in the 2-dimensional, in this case for simplicity, 2-dimensional space, a grid of points where you're going to discretize the equations. So we have 2 Cartesian dimensions, x and y, and we use index I for x, index j for y, and each point in the mesh can be identified by its combination of indices in x and y. So this point in the middle will be point Pij, and you can identify all the points right around them by, for example, in the y direction, j plus 1, j minus 1. In the x direction, I plus 1, I minus 1. So all the points around Pij can be identified with the indices on that mesh. With that, then we can write a finite difference approximation of the Laplacian operator, the second derivative of p with respect to x plus the second derivative of p with respect to y, in this form, where this is the approximation of the second derivative with respect to x, and this is the approximation of the second derivative with respect to y. As you can see here, for example, in all of these terms that appear on this combination, you have only j index changing. J plus 1, j, j minus 1. Only j is changing means only y as a continuum derivative is changing. That's a difference as a derivative with respect to y. And in this part over here, only the index I is changing. I plus 1, I minus 1. So that is actually a differential with respect to the x Cartesian coordinate. Just a quick introduction there to finite difference approximations. So now we have a finite representation of the second-order Laplacian operator on this mesh. What we do to turn this into an iterative method is we pick these terms in the middle, Pij, Pij, and we move them to the left-hand side, and we move everything else to the right. So once you have an initial guess, suppose p equals 0 everywhere. Suppose that you on the right-hand side, you have various values of p on ij minus 1, ij plus 1, and so on. But not this middle point, not pij. That, you leave it on the left-hand side, and you use it as your update. So you're going to update the value of p at ij using all of the neighbors on that initial guess. That is going to be your first update of the field P. Once you do that, and you also have in the full equation some terms that we called B, that you can also, there's B, that you can also represent on the mesh, but they're known, okay? They're going to be known at that point in time, in pseudo time, and you use them in your update. Once you have the update of P on all the points ij, then you do it all over again. You use those values, all the values around every point, all of the neighboring values to calculate Pij for every point on the mesh, and you have your second update. And so on and so forth until when? Well, because the nature of the differential equation, the Poisson equation, is to relax to a steady state, over time, the difference between two updates is going to become smaller and smaller and smaller. So you give your iterative method a target tolerance that is some measure, L2 norm, or some measure of the difference between two consecutive updates. And once that difference is small enough, you stop your iteration. That is called a Poincare-Jacobi method. It's one of the ways to solve a Poisson equation numerically. It's not the best method. It's actually quite slow to converge, and it has several drawbacks, but it works, and we can use it for this example, and that's what we're going to do. We're going to solve the Poisson equation numerically, and we've written some helper functions to do this easy for you. So what is the solution procedure? We start with an initial velocity field that is known, and then to calculate the pressure, here's written out the whole thing that I just described in words. All of the terms that have I plus 1, I minus 1, j plus 1, and j minus 1 have been moved to the right-hand side. Only Pij remains on the left-hand side, and these are all the terms with velocity discretized with their respective finite difference form that were written out for you. Now, once you have an initial guess for P, you can see how you can update all of your values of the pressure for the next iterations, and so on. This is what you're going to be writing in this exercise. Once you've updated the pressure by computing all of the iterations so that P relaxes to its steady state, you have that pressure, and you can go back and calculate the full velocity field that corresponds to that pressure. And that is the procedure that we use to solve the Navier-Stokes equations in what is called a projection method. So because this was too much work for you to do in this session, there are some pre-written functions in this repository for the course that compute all of the update for the momentum equations in the x and y directions. So these are written out for you in this sort of explanatory notebook so that you can study them later if you're interested. But the code for all of this is already provided. What you will want to do is write some code for this part, okay? And a final note that is also left here for you to read if you're interested is that there are a lot of subtleties with all of this formulation. There's issues with boundary conditions that we haven't mentioned, issues with when you apply the divergence of the momentum equation and you cancel out terms, you have some choice of leaving some terms maybe, or and there's been a lot of arguments in the literature about these things. And it's quite fun if you're interested in CFD, but perhaps in this room not everybody's interested, so we just left a tiny note there. This is actually the equation that you'll be interested in today. So that was a breakneck introduction to CFD for today so that you can get a feel for the purpose of this exercise. And for some of you, maybe could be an entry point to do more work later. But with that, I'll invite Gilbert again.
Thank you very much. That is the fastest intro you will ever see to computational fluids. It looks real bad. Granted, we're concentrating on one tiny part of it, but we wanted to, provide some background, so we're not just showing you pretty pictures and saying, look what we did, it's amazing. So the problem we're doing here, this is called lid-driven cavity flow. So this is in 2D. This is a common validation case for solvers. Just imagine you have some fluid in this box, and the lid itself is moving to the left at some known velocity that's constant. And because there's a no-slip condition, we say, which is that the liquid is basically, will move at that same velocity right on the boundary with the lid, it will slowly begin to develop a spiral pattern in the direction that the lid is moving will sort of be the clockwise direction, and then you'll get two distinct pressure zones and pretty pictures. Gonna import NumPy there. Here's this really long equation again. What I will say is that as Professor Barba mentioned, at a given step in the velocity, they are then static as we calculate the pressure. So actually the only part of this equation that we need to really worry about is that first line, so just all the p terms. Everything else we'll calculate once and be done with it until the next time step. And also you don't have to write that because we did it already. But just so you see where it's coming from. So this, in fact, this function velocity term is everything in this pressure Poisson equation below the first line. Right, that's the B that was mentioned in the previous notebook. So we can define that. And then here is in NumPy the pressure Poisson equation. Right, so this is we just have a while loop until we have a while loop. We make a copy of the pressure field as it is. We calculate the new pressure field based on the old one, and we keep doing that until they're close enough that we stop and we say that that's good enough and we move on. There are some boundary conditions here. I wouldn't worry about them for now, or at all, actually. So really, the bulk of it is right here. These 4 lines, that's that pressure update. And then the B function is something we're passing into this. We're calculating it once and not coming back to it. So just to give you an idea of what this looks like, there's this helper function cavity flow here that has all the other velocity equations that we don't need to deal with right now. And I'm using Pickle to load up initial conditions here just so we can compare answers between things and know that we're starting in the same place. So NX and NY here are just the number of grid points in X and in Y. This is a very small toy grid. And then DX is the distance between those individual points that we were talking about in the discretization. Our time step is 0.005, and we're going to run it for 1,000 time steps. So we should end up with something that's roughly 5 time units. And then we're going to, at each pressure iteration, this R tall here, that's basically how much difference we will allow between the 2 successive iterations of the pressure solution before we break out. So having said all of that, we can run this. And you get this, which looks pretty cool. So this is the expected sort of behavior. You can see that you get a high pressure zone in the top right and a lower pressure zone in the top left, and those quiver arrows are just showing the velocity in X and Y around. So it just keeps doing this and gradually drifts to the right. So I'm going to save my answers for comparison later. And so if we run time it on this now to see how long this takes, we get 485 milliseconds per loop. That's on my machine. It may be different on yours. In fact, it will be different on yours. And now we're going to load the line profiler because we want to take a look at how, what's hurting us here. What's the bottleneck, because we definitely don't want to rewrite all of that. And it's tiny. But for any of you who are familiar with Poisson solvers, you will probably not be hugely surprised by the fact that this far right column before the code is the percentage of time spent. You can see that 72% of the total solution time is set just in the pressure Poisson solver. That's the bulk of the computational expense. So that's a good starting point for something you want to improve. right? This is sort of a, we've gone through a rather admittedly complicated setup for this because we want to show you something more like a real world problem, like what the profiling results will look like. And even this is on a small grid. I mean, on a bigger grid, well, all our computers would choke, so we can't do that within a reasonable amount of time. But you can see here that so 72% is a lot, and so that's a good place to start and see if we can improve things. So, since we've identified that the pressure Poisson equation is the bottleneck, we're going to use Numba to speed it up. So you can click on that link to open up the exercise. We've given you some framework here because this is a bit of a beast. So here is this pressure Poisson equation with the while loop, and I have added the boundary conditions in already. I don't want you to have to deal with those. What we want you to do is basically just implement this line up here, right? Where this should actually be, sorry, this is Bij. LaTeX, yeah. So you're being given an array that has shape I and j, as is being grabbed here, and you want to loop over that array in 2 dimensions and basically continuously recalculate p. So note that we're making a copy of p into pn here, so then you can overwrite p, and then you still have something to compare as you continue on. This is the most complicated thing we'll do example-wise, I promise. Does that make any sense? Okay. That is a totally, totally valid response. I'm not going to give you guys like a super long time on this. I don't want you just to sit there and get frustrated on this. I'm happy to walk around and talk people through it a little bit if you want.
Show again the sample version of the code that is not the exercise. So
Right. So the original,
Just recreating that portion, right?
yeah,
just that one portion, and I mean I've
Yes.
yeah.
Right.
Yeah.
So this bit here is already recreated in those 2 for loops in the exercise. And it's just this bit here. This is really, we want to translate, you'll do this a lot with Numba, you want to translate from the array operations to like bad Python code. You want to unroll it. So we want to unroll these 5 lines inside nested for loops, and then see how it goes.
It might help. I don't know if it will, but it might help if you pull up the equation again, just to get a piece of paper and write this down on a piece of paper. You know, sort of large font, so you have it right there. Then look at the maybe copy the piece of code that we've given you. Show it again, maybe. Then copy that piece of code here into a markdown, perhaps, cell on your exercise. So you have it right there, okay? And then where it says your code here, you just want to rewrite that piece of code, but instead of this one that we're giving you, a version that can be accelerated by Numba. Does that make a bit more sense?
I'm going to give you guys about like 10 minutes for this, and then I'll
Yeah, we
release
don't
you
want you
from
to
its,
like really struggle. We just wanted to get a feel for what would be a more realistic exercise with Numba.
in up here, so it's denoting. Well, actually, in here, this is technically incorrect. So, haha, I wrote it wrong. It's denoting, this should be n+1 here, and it's just denoting that so n is sort of the time step or the pseudo time step. So it's basically saying this newest version is a combination of the old versions. Thanks for pointing that out. That was a mistake.
Is the NumPy mean a pseudo substitute? Is there any advantage using mean over 0.25 times 4?
I don't know. It should work. I'm not sure what the if there's a benefit. I mean, it should be translated more or less the same way, actually. But if you get a failure when it runs, then I would take it out in 5.25. Ah, sorry about that. I'm just full of nasty surprises. I apologize. Yeah, of the four pressure variables, not of B, but just of the four pressures. To really make this work, it is a good idea to put a colon after this while loop. That's one of those things you need to do in Python, just generally speaking. Sorry.
Mine has a colon, which is funny.
Maybe I deleted or something as I was going, huh?
No, but
It wasn't in master.
That's just loading the initial condition, so you shouldn't need to touch that part. It'll just run. Oh, it's not loading. Well, that's a problem. My path is wrong. Sorry about that.
Oh, the path?
So you need a dot slash there? Okay, so you can change this, sorry about that, to that. If it's not, I think it actually will depend too on which directory you, okay, relative paths. Okay, guys. I know that was a very short period of time to work on this, but I don't want us to burn too much on it. It sounds like people were interested, though, so that's good. It was a lot of talking. I like it. I also just learned something, which I'll relate to you shortly. It might make you angry. I'm sorry if it does. So this is my answer. So I've just filled in this. So I'm just going, I'm not touching the boundaries. I'm only touching, from the first to the n-1th element in both dimensions. And I just unrolled the loop. One thing that I like about this, if you work with finite differences or something, and you have, if you work with finite differences, is that this notation, even though it's a little more ungainly when you're used to array operations, does actually match the algebraic representation, right? You get p I plus 1j, p I minus 1j, and you can just write that out. So as sometimes those array sometimes those array operations can take some serious thinking, and if you just want to see if something works at all, this may be sort of I would say a good first approximation that might actually be faster than the NumPy version. But in any case, if I run that, you can see that it's the same because there's no assertion failures there with the previous version, and it looks the same, which is a terrible metric, but it is the same. And so now I have 212 milliseconds per loop. So that's actually not like the greatest speed up in the world, right?
45 to what?
To 212. So it's not,
Oh.
right?
So,
But I want to let me move past this just briefly. So if we profile it again now with this new version here, what you can see is that now the percentage of time of the pressure Poisson is down from 72% to 23%. And someone had asked before about like when do you stop? And when you get tired of it, sort of. I mean, but really, in all seriousness, I mean, of course, the time percentages are always going to add up to 100. There's nothing, you can't magically make some of them disappear. So in a perfect world, which this isn't, everything would take exactly the same amount of time, and you just get an even distribution or something. But that's not going to happen. So what I would suggest, we're not going to do this right now or at all. But if you're actually doing this, you optimize one more thing than you should have, but you only know that after you've done it. You keep going until you get reasonable returns on your time investment, until just like breaking out of the loop, you say like, oh, well, that actually only gave me like an extra 2 milliseconds, and I don't care. And that's when you stop. That's when I stop anyway. That's so that's my rough rule of thumb for that. The thing that might make some of you angry, and this is new recently, which is why I didn't know it, but someone just tried, did something. And that works. Sorry.
And the timings?
So it went from 485 to 326. So it's not as fast as the unrolled version, but it is faster than the original version.
And run the profiler on that?
I just added the no Python equals true flag to the original thing without changing anything else, which I should have done anyway. That's always your first step, right?
But see, it's still,
Yeah, so it's not as much of an improvement, but if you wanted to save some time, just add the one line. Sorry?
Instead of doing,
I'm unrolling the loop and writing the four.
Instead of explicitly unrolling the loops, you can also just apparently add the JIT decorator with no Python equals true, and it speeds it up. So yeah.
Slicing wasn't supported in previous versions of Numba. Like doing that kind of moving window average, so you had to unroll. Now you have this really nice syntax. And as long as Numba understands what that syntax is, in the long run, Numba will be able to beat the unroll. Because that's a more compact way of saying, or it's more expressive to use the slice than it is to use that for loop. So in the long run, Numba, that just the JIT, no Python is true, will be faster. Right now, and I would say it's a more idiomatic approach.
okay,
Yeah.
so when they say they support NumPy types, they support the types, they don't necessarily support all the operations that you can do.
Right.
Exactly.
Okay.
Yeah. This is also at my expense, and I'm totally happy with that, a demonstration of just how quickly Numba's development cycle is. So if something doesn't work, you can also just give up and come back like 6 weeks later, and it may just work.
Better to write a tweet
Yeah.
continuum and maybe CC scan
Yeah.
the head guy of Numba and just get a lot of retweets and favorites.
Like, is it embarrassing that you can't do slicing with NumPy arrays?
They have a long list of things that they want to improve.
Yeah.
It's a long list of things that they want. Prioritization partly comes from the community.
Yeah.
How open source.
Show that one line.
Which one? The easy one, or the? Yes, it was actually you just add the same thing. So instead of rewriting the loops, you just add this line, or just at ngit to the original version. Yeah.
So which one what was the fastest one?
The fastest one is still right now explicitly unrolling
But that was
everything.
That was the second. It was a little bit faster than.
Yeah, than the original. So you get. I mean, that is a free speed up for one line. So I would take that, generally speaking. That's pretty good to me.
Yeah, from 75 to 50.
It should drop into no Python mode automatically when it can.
Yes. Sorry, I'm forcing it because if there's an error, I want it to tell me instead of dropping back into object mode. Ngit is just a shortcut for.
Engine is just short for no Python.
Yeah.
So he didn't even need to say that. He could have just said JIT and he would have gotten the same speed.
Yeah.
No Python is just a way of throwing an error if no Python isn't available.
Yeah. I do this by habit just because I want the speed up, and so if I've made a mistake, I want it to yell at me.
Explicitly puts no
But.
Python was true, or he uses NJIT, he's saying he wants an error if it has to be sort of Python.
One more thing that you can do to speed things up, which I've done here, is to unroll the velocity term. Although, given what I've just learned, you may just want to add at ngit to the velocity term on top. What this does give you another speed up if we profile it, where previously the velocity term I think was even with the Poisson, the fast Poisson equation, and now that's made it slower. I understand nothing. Let's just. Something didn't register. We're definitely moving on. Yeah. All right. Someone asked at a break. I'm not going to show this, but I want to tell you guys that it's here. That 5.2 notebook that is optional. One of the questions that comes up a lot is like, is this better than Python, or what if I use Fortran or whatever else? And so I have my best implementations, which doesn't mean the best at all, of Python and F2Py versions of that same problem if you want to compare results. Spoiler alert, Numba's faster. To be fair,
We have a world expert in Fortran here.
I mean, the Fortran can definitely use some improving, and also, for such a small grid, there's a hit just in converting it from the. So I'm sure Fortran's faster. I'm not gonna make that.
You can ask Andre if Fortran code is legit.
Okay. Well, I'll do that when I'm not on camera. How about that? Also, if I have time, I'll come back to it, but they're here and they're well documented for you guys to look at. If you want to distribute Numba accelerated things to people you work with or users or things without requiring them to install Numba. There are in these two number 6 notebooks a new thing called ahead of time compilation, which lets you kind of a la Swig compile your Numba function into something fast that can then be distributed and only requires NumPy as a dependency. So you can remove the need for people to install Numba, which can sometimes be difficult if they don't use Conda. But that's for later if you want. For now, we're going to move to Notebook 7. And this is, I really like this stuff, so I hope you guys find it interesting. So this is how you define ufuncs using vectorize, which is another piece of Numba. So ufuncs are, I mean, all the bits of NumPy that you like are mostly ufuncs. They operate on arrays, element by element. It's all the stuff we use all the time. In the past, if you look at the documentation for how to write your own NumPy ufunc, this is a portion of the example they give you for f of a equals log of a over 1 minus a. And this is just for doubles. If you want it to support other types, you have to add them. And then there's a bunch of wrapper code, and it's difficult. It's all C, and there's a lot of things you have to define. So you should say thank you to the NumPy devs for all of their hard work, because it's really not a small undertaking. We're going to do a runaround on all that, though. If I define this function here, sorry, just trying to move it up here. This is just takes what the sine of a squared and multiplies by the exponential of b. Right? So it operates on scalars a and b here. And so if I give that 1 and 1, I get some answer. I'm assuming this is correct. It's correct. But the math library, as we know, only works on scalars. So if I give it arrays of 1s, it's going to error out on me because it doesn't know what to do with that. So this is where vectorize comes in. Vectorize changes a scalar function into a NumPy ufunc. So if you import vectorize, you can, similar to JIT, use it either in the function call form or as a decorator on the previous thing you've written. So I'm going to create a new function called vectrig using vectorize. And now when I give it AB, it just works. Right? So it's still the same code. It's just, return this trig operation of A and this trig operation of B. And now it works on vectors with one line. Yeah?
So it's like the NumPy's version of vectorize?
It is like, yeah.
Except that it compiles it?
Yep. And so this is what's called a dynamic ufunc. I'll talk a little bit more about this in a second. It just means that I didn't supply a specific signature to it. It'll work with it, whatever I give it. Now, of course, you wouldn't normally write your vectorized functions using the math library because it only operates on scalars. You would just use NumPy, which is what this is. And I'm going to make the arrays a little bit bigger to make it slightly more interesting. So I have just 2 1,000 by 1,000 arrays of randoms. And if I run my Numba version, that's the one I just did, that's 30 milliseconds per loop. If I run NumPy, 32.1 milliseconds. So 2 milliseconds is, not necessarily something to write home about, but the fact that it's faster than the built-in, even by a small amount, is just impressive, I think. So if it's not a dynamic ufunc, you can specify a signature. And what that means is that you're just going to say explicitly, these are the input and output types of what I'm passing in scalar form. You don't need to specify that this is an array or has dimension. You're just saying here that vectorize, and you put it in quotes, that I want an output that's float64, and my 2 inputs are both float64. And you run that on the original trig function. And we should get, hopefully, 30 milliseconds. 30.1, I can deal with that. So that doesn't actually make a difference in the performance. But what it does do, which is, I think, incredibly useful and very cool, is that, and sorry, this line is not Pepe compliant. If you have added a signature, and only if you've added a signature, then you are allowed, and this is just a restriction of Python syntax, you can add the keyword argument at the end here, which is cut off, but which is target equals, quote, parallel. Okay? And then pass it the same function trig. And when you do that, it's actually taking longer, but that's a misnomer. It automatically makes it multi-core. It's for free. You don't have to do anything else. You just add that. So let's split that up. This is on a 6-core machine, 6 physical cores. And that's, what, like a 4+ speed up, just with an extra keyword argument. So someone was asking about multiprocessing, and you can use multiprocessing and JIT, and that totally works, but you can also just do this and not worry about it.
Sorry, can you go into that, or at least, what did you do with that keyword?
Yeah, so if you have an explicit signature, so that float 64, paren float 64, as long as that's there, then you can follow it with the target keyword argument and set it equal to parallel. The default of that is just, I think, CPU, which will run it on a single core and is what is happening by default. If you make it parallel, then it becomes automatically multi-core. And so you'll get not like a linear speed up with the number of cores, but a pretty good one. This is not, yes, sorry.
Can you specify the number of cores you want to run on?
There is an environment variable, which I think is Numba and cores or something. I have to look at the document, but you can specify in the environment to restrict the number of cores. There's also, we're not going to look at this right now, there's also a CUDA target. Stan and Sue are giving a talk later this week on using the GPU capabilities, but kind of in a similar fashion, you can just offload something to a GPU. If it's, I think compute capacity 2 or whatever it is, greater than 2 or something. So most laptops don't meet that. I will also say that, just test out parallel when you're trying things. It's not always the best option. The threading, or the multiprocessing, there's overhead to that. So it's sort of a trial and error thing. If your individual operations, that, the scalar thing that generated this function is expensive-ish, like trig stuff, it's usually pretty good. If it's just A plus B, you're probably better off not doing it unless you're dealing with a really, really big problem, which may be larger than your laptop's memory or something. So I forgot. I think it's multiprocessing, but I don't hold me to that. It's a good question, but yeah.
It's nice that it's a keyword, so that you can make that a configurable.
Yeah,
option
absolutely.
for distributing code for somebody and say.
Yeah, absolutely. If you want something to work with multiple types, but want something to be explicitly, I always want integers back, or you need floor division or whatever. You can specify multiple types like this, where you just put them one after another. The thing to know about this is that they need to go from most specific to least. So if you put, like with the JIT, if you put float 64 first, that's all it's going to do. You need to go from int32 to int64, or if you have int16, you need to put that one first, or it's just going to override them. And if you want to know what it's doing, so you can see here, if I give it, now that I've defined it with integer support, if I give it integers, I just get 2. And if I give it floats, I get what I expect. And there's this n-types attribute, which will let you know how many different integer types are defined for a given ufunc that you've generated. So here's an exercise for you guys to try. We're going to, NumPy already has a clip, ufunc, but we're just going to rewrite it. So you just want to write a function that you send in an array and a minimum and a maximum value of that, and you just want anything that is below the minimum to be set equal to the minimum, anything that's above the maximum to be set equal to the maximum. And remember, you need that vectorized decorator, and also that you're writing this as a scalar thing. So actually, this time, no for loops. Okay, guys, I'm going to keep moving on now so we can finish up. Not finish up, but get to everything I've got, hopefully. So here's my solution. This can take a little, thinking in the scalar way to the vectorized way can take a little practice. So I'm really just, when you define the function, you're really just, you're clipping one value. You say, here's A, I have A min and A max, I want you to, if it's, less than A min, make it A min. If it's greater than A max, make it A max, and then give back A. And I'm doing one in parallel and one without, just to compare performance here. So if we have an array of 5,000 randoms, and I clip between 0.2 and 0.6, then serial takes actually only 6 microseconds, which is pretty fast. Parallel takes 95 microseconds. So here's an example of where those individual operations aren't really expensive enough at this size of array to make it worth it. So this, you just check, and then you see if it's a good idea or not. And then we have a NumPy clip. We can just compare that. And that is the fastest. However, if our array is 100,000 elements, then we get 488 for serial. That's the vectorized serial version. Parallel is now 152, so that's a sort of a large enough array for it to make a difference. And if we compare that to the built-in, that actually starts beating NumPy. I mean, we're using more cores. We have them, so why not use them? So I mean, if you have arrays that are, I mean, there's no good rule of thumb on this, I don't think yet, but certainly 1 million is usually big enough to start having it make a serious difference.
Show again the syntax for the vectorized.
Sure, yeah. So you mean for this particular example, or? Yeah, so sorry it's getting cut off here, but yeah, so you just have to define, I'm just doing it for floats, for doubles here, but you have the type of the output, the types of the inputs in the parens, and then in a second set of parentheses, the function you want to vectorize, or you can just use it as a decorator with everything the same except the @ sign, and you take off the last call to the function, and then if you want it in parallel, just add the target keyword and set it equal to parallel.
But your first input is an array, not a float. Is that correct?
Here, so when I call it, I'm giving it an array, but when you're defining it, you create them as if they're just dealing with scalars. And it's going to operate element by element on everything you give it, but you're just defining the type of a single element that you're going to pass it. Yeah?
What is the usual difficulty if we want to vectorize a somewhat complex Python function, or is it not advised to do that?
It depends. It just depends. This only works element by element. It's element-wise. If it's not element-wise computations, there are other options. But if it's something that, yeah, that you can replace sort of just general NumPy operations with this a lot of the time without too much trouble, and it's often faster. Actually, I have an example of that at the end of this notebook too. I can show you. So now that hopefully we've got a bit more of an idea about how to handle the scalar performance, or how to write it in the scalar form. Why don't you guys try that second exercise? I'll give you a few minutes, just to perform this operation. And you can, I think, if I have an import, just do from math import log. And then, just write the vectorized version of that. Oh, sorry, of the operation there. Okay, guys, I'm going to move on. So here's my solution to this. So I'm just math.log of a over 1 minus a. And then I've just defined like a linspace array there. And good to run the function. Right, okay. This is a mistake, but it's good to point out, actually. So I've forgotten the quotes around the float 64 there. Don't forget quotes. You can actually you can import that type from NumPy or Numba, and it will work otherwise, but quotes are just a safer bet generally. And that works. One last bit on vectorize that's was unexpected when I first came across this, though I wanted to show you guys. If I create like a vectorized function that takes the discriminant of something, so it's just b squared minus 4ac, and I'm not doing any type declaration, this is just dynamic, I don't need it in parallel. And you give it big enough values, which in this case I'm just going to do arrays of 10,000. That vectorized function, the Numba one, will take 12.9 microseconds to do that. And just doing straight NumPy operations takes close to 40. And these are, in one sense, they are simple operations. It's multiplication and addition and subtraction, hey, all of them. And this can be a bit surprising because it doesn't seem like there's that much for it to speed up, but there are a couple things that happen when you have an operation like this one. One thing that NumPy does is it creates temporary copies of sort of these intermediate operations. So it's like b squared, okay, here's a new array that's the b squared, and 4a, and here's 4a, and then 4ac, and here's 4, and then so it keeps making copies. And also it thrashes your cache. It's copying things into and out of cache in a not totally optimized way, whereas vectorize operates element by element, and so gets some speed up from that. So if you do have just mathematical operations you're performing on large-ish NumPy arrays, it's probably worth trying just to drop them into a vectorized function and see how they perform, because oftentimes there's a good speed up to be had there. Okay. Is everybody good on this for now? Cool. All right. So vectorize creates NumPy ufuncs, and they operate element by element. So you get element-wise computations. GU vectorize creates generalized ufuncs, which doesn't have the restriction of it being element by element, but actually you can have something operate on, it's array aware. You can have it operate on elements around an element. So for instance, you could do the Poisson solver this way, because you could say things like I plus 1, I minus 1, j plus 1, j minus 1. That's something that it can understand. There are a couple of important differences between GU vectorize and vectorize. It does require more setup to make it work. So here's an example that I'll walk through line by line to try to outline what's going on here. So I'm using GU vectorize here as a decorator. That's not inherently necessary. It's just what I'm doing here. And there's two parts to this. It's called the signature up here. So one is that I have to explicitly declare both the type and shape of the things that are coming in. So unlike with vectorize, where it's just scalar types, here x is an array, y is a scalar, result is an array. So I need these colons here to denote that I want these to be arrays of int64s and just int64 for the scalar input. And secondly, you need this input-output layout line here. And this is just saying that I have an input of size n, and the empty parens is for a scalar, and those should combine to form an output of size n. Numba needs this information in order to know how to properly allocate things and move them around. And this is a silly function. You could actually just do this with vectorize. I also want to point out that there are no return values when you're using GU vectorize. You pass in the value to be written to. So result in this case is my output. So I want to get that back, but I will declare it and pass it in, and then it will be changed in place. It'll be mutated. So if I run that, so see here, I am just defining an array result of zeros that's in the shape of x, since I'm going to add 1 to everything in x and then stick that as a result. Sorry, add y to it. And then I say result equals g of x, comma 5, comma result. So I'm passing in result, and I'm also getting it out, which I'll speak about in a second too. And so then that's this array operation. Right below it, this works, right? Actually, Numba is smart enough to know that that last argument is the return value. And so if you do not explicitly pass it in, it will work. I don't always recommend doing this because it has, there can be potential pitfalls here. One is that since you're not explicitly defining it and then handing it off to the function, Numba creates it for you, which is very nice of it. It uses empty-like to do that or something like it. And so if you don't touch every element of the array you're passing in, if you don't if that result array that's being generated doesn't get touched somehow, then it's going to be whatever it was initialized to, which might just be junk data that's left over. So especially if you have things like boundaries or, well, mostly boundaries, or just some value that for some reason you're not explicitly accessing inside that GU vectorize call, you don't necessarily know what you're going to get back in that index that you didn't actually put something in. So it can be a little dangerous. It can be also incredibly useful if you're trying to add this into like an existing program you have and you don't want to change every single call of this function you've used GU vectorize on, which is kind of, I think, probably the ideal use case. It's just something to be aware of because it can bite you. Here's a matrix multiply. This is not a very good matrix multiply, but I just want to show it to you guys to demonstrate a little more of the input-output signatures. So here I'm multiplying A times B as matrices, and the output is C. So I have to declare those three things. The last one is the output, and they're two-dimensional arrays of type float 64. And then here's this signature that, if you're familiar with linear algebra, makes a little more sense, where you have an m by n and an n by p input. So you expect an m by p output, where the rows and the columns will collapse that way. This is not particularly fast, actually. Especially if you're using Conda, then you've got MKL backing this up, and their matrix multiply is a lot better than this one that I just wrote. Like vectorize, GU vectorize also supports this target keyword. So if you want to parallelize something automatically, you can do that. In this case, you have to add the signature anyway, so it's not actually that much extra work to stick it in there and see how it performs. I have a feeling that this won't perform very well. We'll find out. Yeah. So again, the same kind of restrictions apply. Like if those individual operations aren't particularly expensive and the arrays aren't really, really big, it's probably not worth it. A lot of this is just trial and error. Does everybody understand the signatures? Does that make sense? They're a little bit confusing at first, I think, but well, let's try. I'll give you guys about 5 minutes for this. This is just this is a heat transfer problem that we're not going to go into too deeply. The code there is complete. All I want you to do is just create the GU vectorize signature for this. So all the loops are already enrolled. So you just want to give it this @GU vectorize, and then just add in the signature of these inputs. So if T, which is a 2D array of floats, alpha is a float, they're all listed there, and then the input-output layout that will make this work. Just looking at what the calls to the function are, try to create the signature for it. And I will leave an example up so you guys have that for reference.
So that
Mm-hmm.
do you have to actually put the right variable names, or is that just?
No, they can be arbitrary, but and actually think, because I was a point I.
Match something in the function?
The output, they don't need to match anything in the function, but the output side of that needs to be made up of things that are on the input side. Like, so you can't have n goes to m. It will have no idea what that means. There are ways to work around that if you need to, but it's kind of an uncommon occurrence.
Can you have things like operations, like n goes to n plus 1 or something?
No, yeah. The only way that I've found to really to get around this, if you need it, is to send in. It's inefficient too, but you send in like empty arrays of the dimension you want. So you say like you give it n and you give it a dummy array n that has dimension p, which is equal to n plus 1, and you send in an empty array of that shape, and you can then use that in the output signature. But you're going to cost yourself a transfer.
We have some special guests dropping in. We want to introduce you to the team. This is Stan and Sue, and this is the Numba team. Are you all blown away by Numba? Yes?
Yes.
Yeah.
There are a lot of other people not here. So.
Yes, of course. But we've had plenty of opportunities to say thank you to the Numba team today, showing all the interesting things. Also, probably from the room, some wish list or feature requests, right?
Yes.
Like you don't have that already piling up.
Open GitHub issues. Even
Yep.
if it's just like, I wish it did blank, I don't, but example functions are really helpful.
And we even discovered some new things today.
Oh, excellent.
Right?
Yeah, I didn't know you guys had added in
Slicing?
better slicing support, so
Yes.
I had an example that was just totally invalidated, but it's fine. It's good.
Oh, okay.
After
So, I mean,
having
so,
to
yeah, it's a
work,
nice
like,
work, yeah.
You've been working for 15 minutes, somebody noticed that you could just add JIT to the top and it all worked.
Ah, nice.
You're deep into Numba's vectorized, and there's discussion about whether you have vector level parallelism coming out of the vectorized functionality. For example, I wrote a vectorized addition operation. Am I going to take advantage of the SSE units?
Right. So we do not have, so the way that you could tell that you probably don't want to do, but you could, is every JIT function has an inspect ASM function that if you want to go, you can scan through and find out when we're at the mercy of LLVM's auto-vectorizer. So for simple arithmetic we found it works. I think we recently fixed something so that division and everything still, sorry, yeah. So basically basic operations will work. Things that will destroy vectorization are special math functions. We don't have a good way. If you call cosine in a loop, you really want like a vectorized cosine. We do not have a library that does that yet. Intel tells us they're working on it, but it's not fully wired in at this point.
But you'll hit the AVX instruction set
If it's there.
if you JIT vectorize.
Yep, yeah. It will auto-detect the CPU and figure out what you can use. And I mean, we verified on Xeon Phi, it'll even do AVX 512 if you're sitting on that kind of a machine.
So inspect ASM is in JIT decorator functions. Vectorize gives
Oh,
you back
sorry.
NumPy U-funcs.
Right, sorry.
You don't have that. But there's an environment variable, number dump assembly, or dump LVM. Either you want to look at LVM IR or the assembly.
There's a section in the manual of environment variables, and you
Yeah.
can look at those.
Yeah, and guys, so the way we looked at the inspect types much earlier today, it's just in the same way, just inspect underscore ASM to look at the assembly being generated.
Would you be able to stick around for a few more minutes while Gil goes towards the last section of the tutorial? It's just the
Yep.
FAQ that he had to the end. And,
Okay, guys, so here is my solution for the signature. So you can see, hopefully, let me get this a little more centered here, that just defining the arrays and their dimension with the bracket colon notation, and then the scalars here, and the scalars also have to be empty parens in that input-output layout. And something I didn't mention actually about vectorize either is that both vectorize and GUvectorize also support the no Python equals true flag, because it will also work in sort of object mode. So if you want to force it into no Python mode, put that in. And then note that it does have to, the output dimensions have to be made up somehow, the input dimensions, or it just won't work. So if you run that, then we can at least see what this looks like. I guess I didn't actually tell you what it looked like, but so this is just a heated plate. It's just a pretty picture. So we have heat being put in along the bottom and the left side there, and then it's just slowly propagating out. There's another example down here that I think I'm going to skip, but you guys are welcome to tackle it in your free time, which is just to this function run FTCS here. This heat transfer thing is looping in time, and I have the loop outside of the GUvectorize function right now. So the second exercise is just to try to put that time looping inside, because you want the loops to not be Python loops, because they'll be slower. But leave that for another time. I did want to just share with you a couple of what for me were questions that I was asking myself a lot, and the answers to them as best I can. One, can vectorize call a JIT function? Yes. That's the first one. So I've got JIT add a plus b. For some reason, I'm calling add from the vectorize. That will work. I think I got that backwards, but does the other way work? Yeah. So you can call back and forth between these. One thing that doesn't work yet, as they stare at me from the side, is that the functions that you decorate with GU vectorize are not visible to things that run in no Python mode. You'll get that error we saw before about no global, this name is not available. So if you need to call a function repeatedly, that for now it's probably best to do that. If you're going to call it over and over again from within a JITted function itself, you probably want to use JIT instead of GU vectorize for that. But if you just have one really expensive thing you want to do once, then GU vectorize is great, and also supports targeting CUDA GPUs. So that's another big perk. This is a little convoluted, but is very helpful, I think, sometimes. Is instance, like, if you want to check on the types of things coming in, doesn't work inside of no Python mode, but you can create these generated JIT things that do support is instance. It's just a little bit of a strange syntax, but you can check, for instance, here the type of some input, and then actually return the function that should be called given these conditional cases. So in this case, if you call like the sum, if you call sum on something that's a scalar, it will usually it'll barf, right? Because that doesn't make any sense. But this is a way to say, if it's an array, return the sum. If it's just something else, this could be much more robust than it is. But if it's not an array, just give me back the thing I gave you. So in that case, I can have it sum up every array, or I can give it a scalar, and it'll still work without crashing. So this is sort of a way to kind of add a little more robustness to your code. Similarly, for something like adding, this would not be very happy if I gave it strings in no Python mode, because it won't work. So here I have add nums, which is in no Python mode, and add string, which isn't. So it'll fall back into object mode and actually work with that. And if I have that defined, then I can, there's this types.opaque, which is just something it doesn't know how to deal with. So if I pass it in strings, it'll call the object mode function that adds strings together. And if not, it'll give me the fast addition of numbers back. So if I give it 3 and 4 strings, I get 34, which is perfectly Pythonic. And otherwise, I actually get addition. So that's a way to kind of handle control flow and stuff if you need to do some checking on things. There are many more environment variables. One that is useful often is to disable the jitting if you just want to try to debug something. This is a quick way, rather than, commenting out all of your decorators or something. You can just set that environment variable, and then it'll all run just as Python. So yeah, if you're trying to really dig into something, this is usually a slightly better way. Finally, these are just common errors that I've run into, and these are from Graham Markall, who used to work at Continuum and now is getting a degree in England somewhere. If you don't have the hide traceback extension installed, I wouldn't run these right now. You can just look at my errors because they're big, and it's hard to kind of keep track of. These are what are called lowering errors. So Numba has to declare the type of the output, of the return value. And so if it can't come up with a consistent type for that, it will fail. So for instance, here I have this getLow function that takes A, B, and C. And C is going to be a bool. And if it's true, it returns A. And if it's not, it returns B. But if I pass in A and B as a scalar and a tuple, then I'm going to get this lowering error. So you see, you can't unify return type, and it says what it's given. It says, well, I've got this tuple of 2 N64s and a float 64. I don't know. I can't declare one thing that covers that, so it's not going to let you. Similarly, if you give it an array and a scalar, it'll say what the problem is. It's saying it can't declare something that's both an array and a scalar. But if you give it 2 numbers, it works, because that makes sense to it. Similarly, I know at least one person got the get adder error. So if you index a scalar, just, these things happen. You write a function, you don't always remember what gets passed to it in every single iteration or something. It'll tell you it doesn't know what that means, because every time when you do this access, it's calling this get item method that doesn't make any sense when you have a scalar. So it'll fail on that as well. One last tricky little thing. When you compile something using Numba, you are compiling it. It's, at that time. And so it's, if you pass a function arguments, that's great. But if you just have something that's a global, it's going to take that global at compile time and stick with it. It's not going to change anything. So if I set a equal to 5, and I have a function that just adds b to whatever the value of a is, then when I run that and I add 7 to 5, I get 12. This is good. If I say now that a is equal to 12, I get 12 anyway, because a was equal to 5 when I compiled that, and it's going to stay that way. So there's two solutions to this. The better solution is don't use globals. It's a terrible idea. I don't know why I did that.
Well, and this is maybe a question for you guys, wouldn't it be just safer to just say, what's A? Like for the function, the JITted function, just say, what the hell is A? Why did you give me something?
So the idea here is that a lot of people use global variables as like enum constants, and so we wanted to be able to inline those. So a lot of people assign constants a global scope and don't ever change them because they're like enum constants.
Yeah.
Yeah, but this is something actually I believe there's a PEP being proposed for Python that'll make it easier for us to detect when globals have changed, so we can go back and
Awesome.
but that's future.
And so until that happens, and if you really want this, you can just force a recompilation. So you take the function that you've JITted and just call the recompile method on it, and then you'll get it with the new value of a. You'll need to do that every time you change the value of a. I don't know why you would do that, but it's possible.
To get like 5 copies of the same function with different variable taken to it?
Yeah, you could do that. It would be better not to do it as a decorator then, and to have it.
And actually, that's a really good use case. We have seen people use this as like function factories. So there, what you often do is define the function inside of a function that returns the function, if that makes any sense. Basically, it's doing a little closure thing. And that's actually a technique we've seen people use to create specialized code for specific uses.
Cool.
So on the GPU targets, is there a way with Numba to test whether GPUs are available, or is the best way to just do a try it, and if it fails, then you have GPUs?
I'm going to throw it at Sue.
There's is available method.
Numba.cuda.
Okay, so there's a test. Go ahead.
There's also CUDA.detect. It's kind of look at if you have, but all these assume you have to have the CUDA driver. If you don't even have the CUDA driver,
The import won't work.
the error is more obscure. There will be an exception.
You'll get an exception that you can catch, but yeah.
Okay, so see if I can get this to work just as one last thing here. Can't see. Oh, God. Oh, no. I don't know. I don't know where anything is on this. I would normally use my terminal. It's not my computer. I don't understand what's going on. Yeah, I know what's going to happen when I click that, I'm running all of this over a VPN and an SSH tunnel. I don't want to touch anything else that's just going to make it break. So I just ran IP cluster, which is what sets up an IPython parallel, like a local network of nodes on my home machine. There's just 4 workers there. And this is just to, I don't know, to end with a bang or something, just to show you. I think it's cool, so that's why I'm showing you. So if you have IPyParallel installed, which I didn't include in the instructions, so right now you may not. So, but you import client from IPython parallel, and you can check that you have actually a number of workers. So I have 4. There's 0, 1, 2, 3. And you create a direct view, which just means I want to talk to all the workers. Then we come back to our famous Mandelbrot function here. So just defining this is the same as in the first JIT example. The way that you use IPython parallel, this is the fastest intro to IPython parallel ever, is you can just add this decorator of @dv, where dv is the direct view I've created of those 4 workers, and say I want it in parallel, and I'm going to block for simplicity, which just means I don't want asynchronous returns. So it's just a decorator. If you want to use it with Numba, it's actually remarkably easy. You just also add that decorator. You know, I don't know what happens if you put the JIT one on the outside. I think it should be on the inside, but it may not matter. Yeah.
You want that.
Yeah, so do it this way. So yeah, then, you know, if I create my mesh grid here. So this is the first one. I'm sorry, you guys can check the notebooks. The screen's just too small to show everything, and I could have put some line returns in, but I didn't. So this is just that original pure Python version running on 1 core. And that takes 910 milliseconds of wall time. I can probably run it a few times and get different times, but it's about there. And then now, this is with IPython parallel, so running with 4 workers. 524 is reasonable. And then this is passing in, using Numba, like the Numba accelerated version that's also been distributed. And that's 358. So you can really start to dig down and you know, squeeze a little bit more time out of these things. I don't know if this is useful, but I thought I would show you because it's cool. And then just to, again, doing our incredibly accurate visual check to prove that these are all the same, I made the figures extra small just in case there's like a dot out of place or something. Yeah, no, mostly I want to show you can stack decorators, which is great. Okay, so that's everything that I have, guys. Thank you so much for coming. There are these optional notebooks that if you want to check out, they're mostly just proof of concept examples for how to use the ahead of time compilation. If you want to, I also have, if you look in the repo, I have a folder with a setup.py to show you how you would bundle, like how you would install using a setup.py, one of those ahead of time compiled modules, if you want to, you know, distribute that with something that you're doing. And also the Numba Python Fortran comparison, which you're welcome to open up issues and destroy my Python and Fortran. I'm happy to hear them. But I still think Numba's faster. And that's it. Thanks so much for coming, guys. Appreciate it.